Okay, as I said earlier this week, I'm just going to release a couple of videos going through some questions from the final two chapters and how to do them. First of all, I'm just going to finish off what we were doing on chapter 20 in Thursday's lesson just by going through some questions from the review set. So this is discrete probability distributions, which is the first sort of half of the chapter from A to C, where it's talking about random variables and the probability distributions for these. And then the second half, I'll release a separate video going through binomial distribution and questions of that sort. So, these are from your review set. I've got a whole lot of questions here. We'll see what we can get through. The first question here says, determine whether the following variables are discrete or continuous. Well, the definitions that your textbook gives you for discrete and continuous are a discrete random variable, x, has set distinct possible values, whereas a continuous random variable can take any value with an interval. So basically taking that mouthful of words and explaining it to you in simple terms, continuous basically means, can I spell today? Continuous means that you're looking at something like a line graph, and it can take any value, x can take any value on that range. So for instance, x could take 0.1, it could take 2, it could take 3.4. Basically, it can take anything. Whereas a discrete random variable, the difference is that it has to take specific values. So, for instance, like a bar chart, how many people do this in one try? How many people do this in 2 tries? How many people do this in 3 tries? We're going to see from the examples that they're giving us here. So, for instance, when it says number of attempts to pass a driving test, I think the average pass rate in the UK is currently 34%, which is very low. But you can still only pass or fail a driving test, and the number of attempts is going to be digit values, 1, 2, 3, 4, 5. You can't have 1.1 driving tests. So therefore, this is definitely discrete. Versus the length of time before a phone loses its battery charge, well, that there is continuous, because you could have 1 second, 2 seconds, or 1 minute, 1 hour, 10 minutes, and 3 seconds, and even within a second, it's continuous, because you could have milliseconds, you could have whatever. And so therefore, that's very much an example of a continuous random variable. And then the final one here, phone calls. Phone calls, you can only have 1 phone call, not 1.1 phone calls. And so therefore, that's discrete. That's a good test, actually. If 1.1 fits as a value for x, then it's probably continuous, versus if it's just 1, 2, 3, 4 digit values, it would be discrete. But quite a common 1-mark question. These are very much non-calculator questions as well, so I'm going to try to do most of them without a calculator. So the next question I've picked off randomly is 3 green balls and 2 yellow balls are placed in a hat. 2 balls are randomly drawn without replacement, and x is the number of green balls drawn. Explain why x is a discrete random variable. Well, it's discrete because it has a distinct set of possible values. So you can even just put distinct. X is distinct. Because you can either have 1 green ball, 2 green balls, or 3 green balls, basically. But in fact, the key part here is that you're only picking out 2. So you can only have 0, 1, or 2 green balls out of 3. So that leads on to part B. State the possible values of x. Well, x could equal 0 green balls, 1 green ball, 2 green balls, not 3, because we're only picking out 2 balls at random. C, construct a probability table for x. Well, if we do that for 0, 1, and 2, that's our value for x, and that's our probability of x. Let's think about it. So we've got to input values into this for all the possible values of x. So what's the probability that we get 0 green balls? They're drawn without replacement, so that means we've got to get 2 yellow balls, really. No green balls, because there's only 5 balls in the pack. So therefore we need 1 yellow ball. Well, the chance of getting a yellow ball is 2 out of 5, because there's 5 balls. And then once we've taken 1 out, we have to do that again without replacement, which is 1 over 4. And so that's the probability of p of x equal to 0. I might get more space here, and we could add a page. So that's first one here is the first yellow ball, and because you've taken 1 out, there's only 4 balls left and only 1 yellow ball left, and so therefore you get 1 over 4 for the chance of the second yellow ball, slightly less. And so that's P of x equal to 0, which is 20, which is 1 over 10. So therefore we can put 1 over 10 in here. That's the probability of that. Probability of x equal to 1. P of x equals 1. Well, to get one green ball taken out, either the first ball or the second ball has to be green. So for the first ball to be green, that's 3 over 5. And then we need a yellow ball, so there's 4 balls left, 2 yellow, so therefore 2 out of 4. Plus the probability of a yellow ball and then a green ball, so that's 2 out of 5 for our first yellow ball. And then what's left over? 4 balls are left over. How many of those are green? 3 of them. And so that's our P of 1. So 3 times 2 is 6 over 20, plus 2 times 3 is also 6 over 20. And so that gets us there to 12 over 20, which simplifies to 3 over 5. Fractions are really handy, guys. Don't add your bottom fractions together. The amount of times I see mistakes with fractions is just unbelievable. But the denominator stays the same. Final one, P of x equal to 2. Means both our balls picked have to be green. So therefore we need a green ball, which is 3 over 5, times the next ball being green. So 2 over 4 because there's 4 balls left. And so therefore we get 6 over 20. 6 over 20 simplifies to 3 over 10. And so let's input these up here. We've got 3 over 5, and then 3 over 10. And they should all add up to 1, and you can check that if you like. Part D, find the expected number of green balls drawn. Expected number, that's just a formula, and the formula is the sum in our case we've got x, haven't we? X of I equals 0 to 2, and you don't have to write this out even, and it's x, let's keep my curly x's, xi times p of x equals xi. That's the definition formally, but it literally just means this one times this one plus this one times this one plus this one times that one. And so therefore what we're talking is we've got 0 times 1 over 10 plus 1 times 3 over 5 plus 2 times 3 over 10. And then whatever that gets us. 3 over 5 plus 6 over 10, that's the same as 2 lots of 6 over 10, which is 12 over 10, which is 1.2. So that's what we'd expect. If we did this 100 times, we'd expect x on average to be 1.2. In other words, 1.2 balls drawn out of it are green. Let's have a look at the next question then. Suppose that x is the number of manuscripts, marsupials, whatever that is. No idea what that is. Entering a park at night. It is suspected that x has a probability mass function, that's just a very long word that you don't need to know anything about, of p of x. I mean, you do that it's probability, but the idea of probability mass functions goes much deeper than what you're going to do. Of p of x equals a lots of x squared minus 8x, where x is between 0 to 8. Find the constant a. Okay, well, the one thing we know about probability functions is that probability, or the sum of p of x, must be equal to 1, or the sum of all probabilities has to equal 1. And so for our case, this is from, write this out formally, like we did for the previous question. If we wrote that out formally, we need p of x equals xi, and then in this case, I is going from 0 to 8. And so the sum of all of those values has to equal 1. I'm trying to think if I need more space here. We're just going to go for it. So if we plug in 0 into this equation, this is just a bit long-winded, we would get a lots of 0 squared minus 8 times 0. And then the next term would be a lots of 1 squared plus minus 8 times 1. And then the next one would be, we're going to get increasingly small here. Let's just change the size. It's good about that. Font size. Change my font size to that. And the next one would be a lots of 2 squared minus 8 times 2. You can see that as the square number is going to get bigger, you're starting to get positive values. So plus a lots of 3 squared minus 8 times 3. Plus a lots of 4 squared minus 8 times 4. All the way up to 8. And then you can just grab your calculator and then just start inputting the values going up from 4 to 8. Or you could try just put it in the summing. That's a good one actually. You could try put it into the sum on your calculator and just take outside a. So either you can use a calculator and you can do 1 equals a lots of the sum between 8 to I equals 0 of p of xi, but p of xi in our case is a of xi to the power squared minus 8 lots of xi. I've taken the outside, sorry, already, but this section here can be plugged into your graphical calculators. I'm going to show you how to do that now actually. Let me get my graphical calculator out. So if I go onto my graphical calculator and then I go to menu and let's find it. There's a way of doing this. I know it. Let's find it. Math. Is it in there? It is. So if you go on to, at least on my Casio, if I go to menu and then I click run matrix, then if I go down to the bottom slide, it gives me the option for math on F4. After I click math on F4, I click F6 to go a little further, and then I click F2, which is my summation sign. And then it'll give you all your different options of what to place in here. I think that will work. In fact, formally writing this is just x really, isn't it? It's just x squared minus that, and it's x from 0 to 8, because that's the values that x can take. So that's what we can input into our calculator. So I'm going to put in x squared minus 8, x, sorry I can't write this down very well for you, but this is literally what I'm putting in. And then I'm going to put in from x equals 0 to 8, and see what that gets me. I get minus 84. So therefore, 1 equals minus 84 lots of a, and so therefore a must equal 1 over minus 84. I think I'm right. There. But alternatively, you could have done it manually, and it would have been very doable. That's an example of a calculated question. There's no extremely hard bit of nifty maths that you're trying to do in here. It's just basically applying stuff to your calculator. It'd be nice to show you my calculator screen, but I can't right now. But that's basically what I've plugged in to my calculator under going to run matrix and then going to math, which is F4, and then from F4 clicking along to F6, and then under F6 you'll find your summation sign at F2, and then you just input all your values like shown. Oh, I'll leave that on actually. So that's part A. Part B. Find the expected number of marisupals, whatever the heck that is, entering the park on a given night. Again, let's show how you do this manually, and then let's show how you do it with a calculator. So again, same thing. From x equals 0, so x lots of p of x equals x to 8, and it's just the sum of x times p of x. So that's basically 0 lots of 0 squared minus 8 times 0 plus 1 lot of 1 squared minus 8 times 1 plus 2 lots of 2 squared minus 8 times 2. Or again, we can just plug this into our calculator, because what is p of x? P of x in our case is going to be x squared minus 8x. And so therefore what we plug into our calculator is the sum from x equals 0 to 8 of x cubed minus 8x squared. And so that's all I'm going to do. I'm even going to go up to my previous sum and just change my numbers there slightly to squared for that one and power of 3 for that one. And I get, a number that I'm not really expecting. I'm trying to think what I've done wrong there. Probability mass function. Oh, I haven't incorporated my A. So that's where I went wrong. Of course, in our probability mass function, we had A, this value here. That's what I forgot. I forgot to do this. So all of that is times by A, of course. So within here, we had A lots of that. Or in each of these cases here, I've missed out the A, like the above line where I've put A in. So you'd really have A times this. And then in the next one, you'd have A times that, basically. So, because that's the definition for P of X. And so in the same way, I can take A outside of my brackets. But what really is our value for A? We work that out in part A. It's minus 1 over 84. So that's minus 1 over 84 lots of the sum 8, x equals 0, x cubed minus 8 lots of x squared. And what my calculator comes out with when I plug this in, exactly the same method as before, doing this lot, is minus 336. And so therefore, let me literally just label all of this as e to the x as well. I should really do that. I should have done that already. Like this. This is e to the x. I will give you these notes as well. This will come up as a PDF on your manage back as well. And so therefore, e to the x is equal to minus 1 over 84. Lots of what I've plugged into my calculator, which has come out as minus 336, which just gets me to 4, because I know my 84 times tables. Joking. Okay, next question, question 10. Consider two spinners illustrated. Okay, they're made up of red and purple bits. Copy and complete the tree diagram, which shows all of that. I'm going to increase my font size now. Pentagon spinner, square spinner, all the possible results when two spinners are spun together. So they've just defined it as red and not red. Let's do the same. Red, not red. The little line means not red. And then it was my pentagon, and then my square spinner. And then this one here is the same, red. Not red. Red. Not red. So, the chance that my pentagon spinner is red, I'm looking for this panel, and this panel out of 5. So that's 3 out of 5. So probabilities have to add up to 1, and so therefore the other one's 2 out of 5. We could have counted that there's 2 purple spinner bits. Same thing here, 1 over 4, 3 over 4, 1 over 4, 3 over 4. Great, that's part A. Part B. Calculate the probability that exactly one red will occur. Exactly one red is going to be going down this line and then down that line, or going down this line and then up that line. So, as when you're working with tree diagrams, you just multiply the probabilities along the columns. So 3 over 5 times 3 over 4, and then this one here would be 2 over 5 times 1 over 4. And then you just add those together. So 3 over 5 times 3 over 4 gets me to 9 over 20, and then 2 over 20, which is the same as, 1 over 10. But it's easier if I keep them over 20, because then I can add them together using the power of fractions. 2 over 20 gets me to 11 over 20. And that's P of, oh boy, P of R equal 1. P of R equals 1. Or P of red equals 1. There's one red. Okay, part C. The pair of spinners is now spun 10 times. Okay, let X be the number of times that exactly one red occurs. X be the number of times that exactly one red occurs. Okay, the probability of one red is 11 over 20. If that's spun 10 times... Oh, we're now moving to binomial. I don't want to touch that yet. We're doing binomial in the next question. But basically, it's rolled 10 times. What's my number of trials? 10. And then, what's my probability of success? 11 over 20. And you could do binomial with that as part C onwards. But we're not covering binomial in this video. Binomial's next video, although it's kind of related here. Now we'll do it next video. This is specific to discrete random variables, but discrete probability distributions, sorry. Okay, review set B. Show that the following are valid probability mass functions. Well, the only way to tell if something is valid, same as an earlier question, is if the sum of P of X equals X equals 1. So the sum of probabilities equals 1. That's the only definition for a probability mass function. So we need the sum of, for part A, we need the sum of P of X to equal 1 from X equal from, I don't know, whatever X is equal to. In this case here we've got X from 0 to 1. So what we mean is that the sum of P of X equals X needs to equal 1, so we need E of 0 over 1 plus E of 1 over 1 plus E to equal 1. Well, E of 0 is just 1, and E of 1 is just E, so therefore I get 1 plus E over 1 plus E, which equals 1. So that's definitely a probability mass function. Second one, P of X equals X squared plus X over 40, so I need the sum up to 4, so I might as well write it down now. X equals 1 to 4, P of X equals X, which in our case means that we need all of these to add up to 4. Again, you could use a calculator and just plug in the sum for X equals 1, X squared plus X over 40. Exactly like we've been doing. Very valid, very easy to do, but in this case here it's a proof, and so I'm going to write it out because I think that's probably what they want, if it's to show that. Showing on your calculator doesn't really count because you're not like taking a picture of your calculator and putting it on your test paper. So let's put in 1 here. We've got 1 squared plus 1 over 40 plus 2 squared plus 2 over 40 plus 3 squared plus 3 over 40 plus 4 squared plus 4 over 40. Let me put that down. And I'm just going to check that those equal 1. So that's the same as 2 over 40 plus 6 over 40 plus 12 over 40 plus 16 plus 4, 20 over 40, which does indeed equal 40 over 40, which is 1. Great. Question 4 on that review set 20 part B is P of X equals that, where this is a probability mass function. I remember I just saw that one actually, and I remember why I pulled it off. The reason I pulled this one off is actually because you're going to use a bit of geometric sequencing, I think, to show that. Because in the same way, we know that the sum of P of X equals X, in this case, has to equal 1. Well, what values can X take? X takes all the values from 1 to infinity. That's what the ... means. It just continues on. So we need the sum of all x's, p of x, x equals x's, from 1 to infinity to equal 1. Well, how do we do that? At first, it kind of stumps you until you realize that this format here is exactly the same as a geometric sequence. So let's show that. So therefore, if we've got the sum to infinity, x equals 1 of 1 over 3, a to the x minus 1. The difficulty here is that you couldn't use your calculator in the same way that you want to with this because of the a being the unknown here. If that was a number, very simple, but it's not a number. And anyway, your calculator hates doing things to infinity. Okay, so, and there's a reason for it. It would probably crash and you'd kill it if you tried to do a calculation like that because it would die trying. So in this case here, let's think about what this looks like. I'm going to take my third out because you can do that with summations. I actually really like summations, they're quite fun. To the minus 1, and then think about what we recognize here. In fact, I can even leave the third inside, I've just realized that. Why can I leave the third inside? Because does this remind you of anything? Yes, it reminds me of something. It reminds me of the sum to infinity of x equals 1 to infinity of ar to the n minus 1, or a geometric sequence equals a over 1 minus r. And so it's n equals 1, isn't it? Whereas we've got x. And this here is just straight off your formula booklet. I've not taken that from anywhere. That's from your formula booklet. So this is formula booklet. For the sum of a geometric sequence. And so what's my a here? Well, in this case here, a equals a third, and r equals a. And we know that all of that equals 1. And so therefore I know that 1 over 3 over 1 minus r, which is a, equals 1. And then let's just solve for a. So that means that 1 over 3 equals 1 minus a, implying that a must be 2 over 3. That, I think, is quite a cool question, but also quite tricky. So that's why it's probably helpful to watch this video. Because a one like that, I think, unless you were sort of really in the zone of geometric sequences and everything else, you might not necessarily spot that a probability question would incorporate that. Explain why the mode of the distribution is 1. Okay, let me think about it. Why would the mode of the distribution be 1? That's a really strange question. Why would the mode be 1? Well, let's think about the probabilities that we're going to get out of here. So P of x could take the values. I'm just sort of spitballing here, but let's see what comes from it. Could take the values from x equals 1 to 3 and onwards. Well, 1 over 3 times a, which is 2 over 3, to the power of 1 minus 1 would be your first term. Your second term would be 1 over 3 times 2 over 3 to the power of 2 minus 1. And this here is all for 1, 2 as our x values. 1, 2. For 3, the probability would be 1 over 3 times 2 over 3 to the 3 minus 1, so on and so forth. So let's see what those get us. So 1 minus 1 is 0, so anything to the power of 0 is 1, so 1/3. 2 minus 1 is just to the power of 1, so that gets us there to 2 over 9 lots for x equals 1, 2, 3. This next one's going to be squared, so that's 4 over 9. This is 4 over 27. And so what I'm going to assume is that all the probabilities here are getting smaller. So probabilities getting smaller. Probabilities getting smaller. And so what's the mode? Hey diddle diddle, the median is the middle, you add and divide for the mean, the mode is the one you see the most, and the range is the difference between. So the mode is the one that you see the most. That's just a fun rhyme that I teach to the NY1s. So which one do you see the most? Well, it's the one with the highest probability. What's the one with the highest probability? That is your highest probability. Everything's getting smaller. And so therefore the mode would be 1. So puppy, the mode. Great. Last question. It's probably going to be quite a long video. Last question. Suvi plays a game. She's got 2 coins and a set of bowling pins. This is the very last one on the chapter. The coins are flipped, number of heads, results, blah, blah, blah. Let me start highlighting stuff as I go through. She plays a game involving 2 coins and a set of bowling pins. I'm trying to think, are there 10 bowling pins? It might be significant. The coins are flipped and the number of heads, the result is the number that she attempts to knock down with the bowling pins. Okay. If she knocks down all the pins down in one given attempt, it's called a strike. Okay, fine, obviously. All the pins down. Suvi wins a $10 prize by the number of strikes she gets. On each attempt, the probability that Suvi gets a strike is 1/3. Okay, that's probably key as well. $10 prize, I'm not sure we're going to use that, but we might use that. Okay, copy and complete the table diagram. Okay, well we can do that. So let's see where we go. So, probability of rolling a head is a half. Probability of rolling 2 heads is a half times a half is a quarter. Probability of rolling 1 head, well, 1 head would be, 1 head would be either you get a tail and a head, or a head and a tail, so it's a half times 2, so it's basically 2 over 4, or a half. And then the final one here is 0 heads. Again, the probability of getting both tails would be a half times a half, because a tail has the probability of a half. So that's 2 heads, 1 head, 0 heads. And then possible outcomes. This is the part where I'm now slightly stumped. Strikes, 2 strikes. Let's write them down anyway. 1 strike. Or 0 strikes. 1 strike, 2 strikes. Or 0 strikes. That's why I should probably prep questions in advance. Flips the number of heads she gets knocked down the bowling pins. Number of attempts she gets to knock down the bowling pins. Oh, on each attempt, the probability she gets a strike is 1/3. Okay, fine. I've seen that now. That's why it's good to highlight bits in the question. So 2 strikes is 1/3 times 1/3 is 1/9. 1 strike is 1/3 times 2/3, which is 2 over 9, but that times 2, which is 4 over 9, because you can either have a strike, not a strike, or not a strike, and then a strike, if that makes sense. So that's 4 over 9. And the probability that she doesn't get any strikes would be 2 over 3 for not getting a strike, and 2 over 3 again, so that's 4 over 9 as well. Great, I kind of get this. And then probability of a head, and then 1 strike. A head and then 1 strike. Coin to flips, number of heads resulted. It's the number of attempts she gets. So she's only got 1 attempt, so therefore 1/3 is her 1 attempt. And then 0 strikes. Well, whatever's left, 2/3. And then 0 heads, well, she gets no strikes because she has 0 attempts. That is a really strange question. But that's what I mean. It's probably good to go through these ones because quite often the textbook gives you some proper weird ones. And to be honest, the textbook is not quite as quality as an exam paper would be. So questions can often be a bit misleading because nobody's really had them double-checked. They might be double-checked, but it's not the same way. It's like the poor guy that has to write a question on your textbook probably gets paid 10 pence per question versus getting to write an exam question, probably get a few £1,000, I reckon. I don't know. It's a bit of a difference. But that's our diagram, tree diagram. B. X. Let X be the number of strikes Susie gets. So 0, 1, 2. 0, 1, or 2. Find the probability distribution of X. Okay, well, the probability distribution of X is going to be like that. And so therefore we've got 0 strikes, 1 strike, or 2 strikes. Don't really need the final line, so let me just get rid of that. And then this is the probability of them. Probability of X equals to X. Sorry, this really should be small x everywhere. And so P of X equals 0. Well, P of X equals 0 would be going down this line, and then this line, and then this line, and that line, and then that line. So let's multiply probabilities together for a bit. Okay, now we've done that, we can add those together. So common denominator would be 28. And so, 36. 4 times 9 is 36. And so therefore, let's get them all over 36. First one would be 4 over 36 plus 12 over 36 plus 4 goes into 36, 9 over 36. So 4 plus 9 plus 12. What I'm basically doing is converting them over 36, so I can add them. So let's write down 4 plus 30 over 36, 12 over 36. Again, this is where your fractions comes in handy. Definitely worth revising that. And so if you add those up, you should get 25. So it's very high, actually, that she gets nothing. Okay, probability of 1 strike, well, that's going like that, or like that. Again, just multiply them along the rows and columns, you get 1 over 9 here. And then for this one here, I'm going to get 1 over 6. Common denominator of 6 and 9 is 18, because both 6 and 9 go into 18, and so therefore this here would be the same as 2 over 18 and 3 over 18. And so if we add this together, we get 5 over 18. And then the last one, 2 strikes, that's probably going to be the rarest. We can almost expect that because you've got to go along this line and that line, and there's no other way of doing it. So that's 1 over 36. You can always check by then adding up all of these probabilities, and it should equal 1. Part C. Calculate Suvi's expected return per game. Prize is worth $10. Wrote that down earlier. Multiplied by the number of strikes she gets. Okay. $10 multiplied by the number of strikes she gets. Okay, so so basically this is worth $10 if she gets that one, and this one here would be worth $20 and $0. Okay, so to find the expected number, I'm going to do 0 times 25 over 36 plus 10 times 5 over 18 plus 2 times 1 over 20 times 1 over 36. And that gets me to 50 over 18 plus 20 over 36. That's 120 over 36. And so that gets me to 36 goes, whatever, 3 times into that. Not quite. Okay, 3.3 recurring. And so therefore, what's the expected return? It's going to be 3.33 and onwards dollars. Let's put that to 2 decimal places because you don't have dollars past 2 decimal places. Okay, so, I mean, it depends how much she's paying to play the game, but $3.3. Find Suvi's expected gain if the game costs $5. Okay, I thought they'd do that. Would you advise her to play the game? Many times. Okay, part D. Expected gain would be $5 minus $3.33, which is $1.67. So would we advise minus $1.67, sorry, wrong way around. So in other words, she's losing money. So would we advise her to do it? Definitely. Because we're mathematicians. We don't believe in logic. So then you could put down definitely lots of times Suvi should play the game. Play the game. Lots of times. Or not at all. Okay, that's the first half of chapter 20. Please go through those questions. I've tried to pick them out so that it goes through everything you could possibly get of these type. And I'm going to release the other one shortly now as well.